All right, we're going to start this video by finishing up one that you're going to try on your own. So here, this is my one-to-one. Let me zoom in just a touch. This is my one-to-one property of logarithms. I have one log equals another log, and they both have the same base. You can't see it. It's called the common log, but it's an invisible base 10 when you don't have the number written there for the base. Bases match, so I can ignore the bases. Solve whatever type of equation I have for the arguments. In this case, it's linear. I'm going to subtract x from each side. And I will subtract 2 from each side. So this becomes 4x on the left and positive 8 on the right. Divide by 4 and I get x equals 2. And then with logarithms, because of the domain restrictions, I am going to check. So I put a 2 here on the left, and I've got log base 10 of 5 times 2 plus 2 is 12. And that equals log base 10 of 2 plus 10 is 12. So those match. The arguments are positive, so they work out fine. The last one, I'm gonna skip this one. The last one here, what's different is you have 2 logs on the same side. All right, so that's what makes these different. So far, if I look up here, the first page in this example had a single logarithm. We'd switch forms. Here, on these two, we had a logarithm on the left equaling a logarithm on the right, and they had the same base. Now we have 2 on the same side. So it's going to take a different strategy. I mean, just recognizing the type tells you or helps you decide on a good strategy. So the last class, we found out that when we are adding two logarithms with the same base, that can be expressed as, let's see, I think this was how I think that's how they wrote it. So if we were adding 2 logarithms with the same base, that would equal 1 logarithm of the product of those arguments. And it was called the product rule. So we're going to apply the product rule here. We're going to combine these together, and then we'll have a single log. More like maybe this one up here, so we can rearrange it as an exponent. So I'm going to go ahead and multiply the argument. So I have the log, using the product property, of 2x times x minus 5. So I'm going to multiply those together, and that equals 2. So now I have a single log. I'm going to go and distribute that. So I have the log base 10, or the common log, times of 2x squared minus 10x, and that equals 2. So now I've got a single logarithm. So this now becomes the strategy of these two up here previously. So I'm going to rearrange it. Log base 10 of this equals 2. So 10 to the second power squared equals 2x squared minus 10x. This is 100, so I will go ahead and subtract 100 from each side. Make that a 0. Divide everything by 2, and I recognize this is a quadratic. And now I'm going to try to factor. I could use other methods as well, but typically the book is nice, and they want us to practice factoring, so typically these can be factored. So things that multiply to 50, negative 50, and add to negative 5 would be negative 10 and positive 5. And zero product property tells me that here x will be 10 and x will be negative 5. But these are only possible solutions. They're not guaranteed, because I do need to check for extraneous solutions. Just make sure I'm not creating any domain restrictions. So here, if I plug a 10 up to the original, this would be log base 10 of 20 plus log base 10 of positive 5. And that equals 2. And I could work that out, and I would find that that equals 2. So 10 is going to work. If I plug in a negative 5, I get log base 10 of 2 times negative 5 is negative 10. So I'm now taking the log of a negative number, and that's not possible. There's no power of 10 that would equal a negative 10. That's not going to happen. So this one does not work. Okay. This one forces us to take the log of a negative number. And that's not allowed. That's not part of our domain. So we're going to throw this one out. It's called extraneous, and we'll keep x equals 10. That's the only solution. Let's see what's on the next page. So there's a couple here that you could try, which I recommend. They have answers here to check, which is pretty great. It looks like this one will probably be a quadratic, and maybe this one too. So 7 and 8 would be really good for quadratic practice. And you'll probably get an extraneous because I see that nothing here has two solutions. So you could try those on your own, but let's go ahead and do this. This is an inequality, and the reason, if this were an equation, I would just try to change the form and that would work out fine. But because this is an inequality and one side is less than the other, right? It's not an equation where you can flip sides and it stays equal. The left side needs to stay less than, and the right side needs to stay greater than. So I can't just rearrange these things. So what I'm going to do is use an inverse property. I found out a couple days ago that the inverse of 3 to the x, a base 3 as an exponent, is a logarithm of a base 3. So if I rewrite this, if I take the log, right, so I'm going to take the log of both sides. I'm going to take the log of both sides. So I do a log base 3 of 3x is less than the log base 3 of 20. Because my bases match, these are inverses of each other. It's an inverse property. They're going to cancel each other out, and it'll leave just the power of x. And so I've solved it in really just one step. That's the exact solution. You can also use your change of base formula to get an approximation. So it would be the log of 20, the common log of 20, divided by the common log of 3. So it's 2.727 approximately. Right? So if we have an exponent with a base we're trying to get rid of, we can go ahead and take the log of each side. So here it's a base e, so I'm going to take the log base e, called the natural log. So we're going to natural log both sides. So I'll have the natural log of e to the x plus 5 is less than the natural log of 36. The natural log of e, these are inverses, they cancel, so I have x plus 5 is less than the natural log of 36. Just subtract 5 from each side, and I've got my inequality. Nice, so now we can use logging of both sides to get rid of a base that we don't want. The same is true if we have a log and we want to get rid of a log with a base we don't want, we can exponentiate both sides. And what that means is, this is a base 10 here. So we're going to I don't know if I can spell this one, let's see, exponentiate, that's a real thing, exponentiate both sides. And that means write both sides as the power of some base. This is a log base 10, so if I make that the power, the exponent of a base 10, like that, and I exponentiate the right side as well, so it's 10 to this is less than or equal to 10 to that. Now I have an inverse property here where the log base 10 is in the power of an exponent with a base 10. These are inverses, they cancel each other, so I have x is less than or equal to 10 squared, which is 100. So again, in one step, you can exponentiate both sides and it disappears. This will be the last one. The natural log of 2x is less than or equal to 4. So again, this is a base e. It's the natural base. So you can't really see it, but that's what ln means, the log base e. So if I exponentiate both sides, so I write a base of e on each side, and then write this as its power, like that. Now I have an inverse operation on the left side, right? The goal is to get x by itself, and this inverse operation gets rid of the log, and so I have 2x is less than or equal to e to the fourth. So my last step would be divide both sides by 2. And I'm not sure how the book might like to write it as a fraction there. Instead of dividing by 2, might like to write multiplying by 1/2. Either way, these are equivalent. If you had to divide by a negative number, you would flip the signs just as usual, but in this case, I divided both sides by a positive 2, so I left that. So hopefully that's a good start, gets you a great head start on your homework. If we have time, there's about 30, I want you to have 25 or 30 minutes for the quiz. If there's time prior to that, it'd be great if you spent a few minutes working with a partner to try to solve these problems. Best of luck, and I'll see you soon. Let me know if you have questions.